We know that the average speed of light is less than c in a transparent medium. How much less depends on the nature of the medium and on the frequency of light. The speed of light in a transparent medium depends on its frequency. Violet light travels about 1 to 2% slower in glass or water than red light. Light waves with colors between red and violet travel at their own intermediate speeds. So light refracts by different amounts according to frequency or color. We see white light encountering a glass prism. At the first surface it refracts, with blue refracting more than red. The two colors separate. When emerging, light undergoes a second refraction and the separation is further increased. This separation of light into colors arranged according to frequency is called dispersion. It's what enabled Isaac Newton to form a spectrum when he held a glass prism in sunlight. Dispersion also occurs in water, where violet light is slower than red light by about 1%. A most spectacular illustration of dispersion by water is a rainbow. For a rainbow to be seen, the sun must be shining in one part of the sky, and water drops in a cloud or in falling rain must be present in the opposite part of the sky. When we turn our backs toward the sun, we see the spectrum of colors in a bow. Seen from an airplane near midday, the bow forms a complete circle, with the shadow of the airplane in the center. All rainbows would be completely round if the ground were not in the way. Here we see refraction and internal reflection in a sample water drop. The illustration shows only the red and violet rays. All the other colors are in between. This is one of millions of tiny spherical drops that act like prisms. Follow the ray of sunlight as it enters the drop near its top surface. Some of the light is reflected, which we don't show, and the remainder is refracted into the water. At this first refraction, violet deviates the most and red the least. Reaching the opposite side of the drop, each color is partly refracted out into the air, not shown here, and partly reflected back into the water. Arriving at the lowest surface of the drop, each color is again reflected, not shown, and refracted into the air. This second refraction is similar to that of a prism, where refraction at the second surface increases the dispersion already produced at the first surface. After two refractions and a reflection, the outgoing light can make an angle with the incoming rays of anywhere from 0 degrees to a maximum of 42 degrees, depending upon where the light strikes the droplet. For a head-on ray at the middle of the droplet, the light is sent straight back for an angle of 0 degrees. Light striking near the edge of the droplet makes an angle close to 42 degrees with the incoming light. Although each drop disperses a full spectrum of colors, an observer is in a position to see the concentrated light of only a single color from any one drop. If violet light from a single drop reaches the eye of an observer, red light from the same drop is incident elsewhere below the eyes. To see red light, one must look to a drop higher in the sky. The color red will be seen when the angle between a beam of sunlight and the light sent back by a drop is 42 degrees. The color violet is seen when the angle between the sunbeams and deflected light is 40 degrees. Why the bow shape for a rainbow? The answer to this involves a little geometric reasoning. First of all, a rainbow is not the flat two-dimensional arc it appears to be. It appears flat for the same reason a spherical burst of fireworks high in the sky appears as a disk, because of a lack of distance cues. The rainbow you see is actually a three-dimensional cone with a tip, apex, at your eye. Consider a glass cone, the shape of those paper cones you sometimes see at drinking fountains. If you held the tip of such a glass cone against your eye, what would you see? You'd see the glass as a circle. Similarly for the bow shape of a rainbow. Only raindrops along the dashed line disperse red light to the observer at a 42-degree angle. So there's a geometrical reason rainbows have a bow shape. Often a larger secondary bow with colors reversed can be seen arching at a greater angle around the primary bow. We won't say more about the secondary bow except to say it's formed by similar circumstances and as a result of double reflection within the raindrops. Because of this extra reflection and extra refraction loss, the secondary bow is much dimmer and its colors are reversed. Another thing, whether a single or double rainbow, your cone of vision that intersects the cloud of drops that create your rainbow is different from that of a person next to you. This is a rainbow as seen from my brother Steve's home in Costa Rica. If he says, "Look at the yum rainbow," you can reply, "Okay, move aside so I can see it too." Everybody sees his or her own personal rainbow. I want to leave you with a question. If light traveled at the same speed in raindrops as it travels in air, would we still have rainbows? Defend your answer. Until next time, good energy.